from tables. Now, in tomorrow's class, we are going to bring back EVT, the extreme value theorem. Tomorrow, we're going to talk a little bit more about the other two existence theorems. So that'll be in tomorrow, but they also utilize them. The main premise for them is going to be tables. So I wanted to cover the idea and the premise for tables, and what we do know and what we don't know, and why. They're very common free response and multiple choice type questions on the AP exam. So first and foremost, given that f of x is continuous on the closed interval a to b, what do we know? Well, first and foremost, what we do know so far is that without any actual, you know what? I'm actually gonna go in to it. I'm gonna switch up a little bit. Even though I'm gonna ask some of these questions tomorrow, I do want to go into those. But I won't. I'm not gonna do too much. So I'll just introduce IVT and MVT more precisely. So basically, all we know is A, B, and we know, of course, therefore, f of A and f of B. Now, we don't know what happens within here. We don't know any other specific values within. However, existence theorems will hold true. So, existence theorems. Well, we know the first one, which is the extreme value theorem, EVT. And EVT, the extreme value theorem, informed me that given that there's a closed interval, all right, given that we have a closed interval, we know the function is closed, then we know for certainty that there must be a point f of c for c less than or equal a less than or equal to c less than or equal to b that is the absolute max, and f of k such that, or for a less than or equal to k less than or equal to b, that is the absolute min. So we know that there must be a point that is higher than any other point, and we know there's a point that is smaller than any other point as well, somewhere on this interval. At least once. So at least once there's an absolute maximum somewhere. At least once there's an absolute minimum somewhere. Okay. The next one, and I'm going to introduce it today. The next one, and usually we teach these in the reverse order, but I like them doing this way. I like the existence theorem first. The next one, yeah, you know what? I should have probably, and if I can go back, now that I'm going through these lessons, I'd probably rotate, but it doesn't really make much of a difference. It's called the intermediate value theorem, also known as IVT, and I'll get into this a little bit more tomorrow, like I said. So we have EVT and then IVT. IVT states that every value between f of A and f of B must occur at least once. Okay. Now that's just the basics of IVT. So basically what IVT is saying is that, okay, I have A, I have B, and I have F, and actually let me switch up this way this graph looks. Let's say, for example, F of A is down here, and let's say F of B is up here. So I know this point exists here and this point exists here. It doesn't matter if f of A is smaller or f of B is smaller or bigger. The idea, we have two values. And so what IVT says is that every value between this must happen at least once. It can happen more. So for example, the main premise for IVT, the main usage for IVT is the value of 0, the x-axis. And this is kind of what we had gotten when we talked about relative extrema. If you go from negative and then you go to positive, it's kind of like the reverse part of what we've been doing. If you go from negative to positive, then at some point, you had to cross 0. If you go from positive to negative, when we're talking about the sign of the derivatives, then at some point you had to cross through 0, given the function was continuous. So that was the main premise behind those, is that every value, so the value of 1, the value of 2, any value that's between f of A, so, i.e. by IVT, since f of A is less than 0 and f of B is greater than 0, then f of x equals 0 at least once for x value between A and B. So for some value, I don't know where it happens, but I do know it must happen. And it's kind of like a no kidding type of thing. The IVT is one of the most obvious theorems, the rules that we have in calculus. Sometimes we even put it down inside an advanced algebra, or most likely a pre-calculus. IVT is usually the one that's actually covered in pre-calculus typically. All it says that, hey, if I go from here and, I don't know what happens, but given that I have a function, let me actually erase that last part. So I don't know what happens, but at least once, no matter how I connect the dots, since the function is continuous, then I must cross every single value must cross at least once. That's what IVT says. The third existence theorem I'm not going to cover the third one, but I'm just going to state it. I'm going to put a little star on there. It's called the mean value theorem. And I'm going to put a little star for IVT as well, because we're really going to cover these tomorrow. But in terms of giving a little bit more thorough put examples, but I kind of want to put at least the premise out there to do the work that we're doing. MVT specifies that f of x, if f of x is twice differentiable, which just means that f of x is continuous on the closed interval a to b and differentiable on the open interval a to b. You'll see this twice differentiable, which just means that the derivative itself is continuous. All right, no sharp turns. That's all it really means. Then there must exist at least one point where the derivative at the point C is equal to f of b minus f of a all over b minus a, for a less than or equal to, for a less than b, or actually less than or equal to c less than or equal to b. Now I'm going to go into the IVT and MVT more tomorrow. Okay, so today is almost like two lessons unto themselves. So tomorrow's focus is on doing problems with MVT and IVT, as well as the tables and how EVT can show up in terms of our knowledge for those problems. But we have here the existence theorems, and each one of them says that at least once it happens. Now, it can happen more than once. There could be more than one time. There could be, just like for the absolute maximum, the absolute maximum can occur at 2 different x values. It could happen at 3 different x values. But we know there is an output that happens at least once. IVT says that the function must take on every value within there, at least between f of a and f of b, at least once. For the example in the picture, 0. Now the function can equal 0 more than once, but we know by the IVT, but it just says that it has to happen at least one time. At minimum, one time it occurs that it crosses y equals 0. And MVT just says that the average rate of change, and like I said, I'll get into this a little bit more detail. It says that the average slope, that the tangent slope will equal the average slope at least once. I'll go into there. The existence theorems are all based on the premise of at least once there exist, hence the existence theorems. Now, what we're going to focus on today, though, is kind of utilizing the premises of these, but I'm going to focus it on a little bit more, and I want to say layman's terms, but in terms of a little bit more direct teaching for tables. Because basically with tables, we're going to look at tables which are intervals. Actually, I don't know why I shifted that over. Tables are like, it's a terrible way of saying, tables are closed intervals with many closed intervals within. We often call these many closed intervals partitions. in calculus. PAR. What do I mean by that? Well, for example, i.e., in example, if I gave you the table for the x values and the output values, and I gave you 1, 2, 4, and 5, all right, and this is whatever f of 1 is. I give you f of 2. Let me just give you some numbers here. And we have like -1, 3, 5, -6. Now, this interval is the closed interval from 1 to 5. But we have little mini intervals within. We have the interval 1 to 2, 2 to 4, 4 to 5. Now, you can also argue that you have the interval 1 to 4 and 1 to 5 as well. And the interval 2 to 5. So you have all these little intervals. And most of what our focus and view on will be, most of our view and focus will be on the basic intervals. So we just go this interval, this interval, this interval right there. We'll view the big interval, but what we're going to actually be doing is we're going to say, okay, between 1 and 2, what must occur? Between 1, 2, and 4, what must occur? Between 4 and 5, what must occur? And that's what we're going to focus on. We're going to focus on these little slopes, these little intervals that happen, and the premise behind them. And I don't really want to. I'm not going to try to really plow it through in terms of MBT and so forth and IVT. The premise of it, though, comes from those, and that leads us to today's material, which is the idea of inferences on tables. And what we're going to focus on the inferences in today, we're going to focus on slope and concavity. Okay? And so what we and to do these problems for each partition, we can calculate the average rate of change, the AROC, / slope, and infer what must and what could be true. So I want you to note that the biggest mistake is believing blah has to happen. Likely, it could happen in these problems. We don't know, and here and I want to take a little bit of time to talk while you're writing this down. So between the interval of 1 to 2, we know the function goes from -1 to 3. But because of kind of like because of EVT, that doesn't mean that the function cannot be lower than -1 or higher than 3. It is possible that the function goes higher than negative or lower than -1 or higher than 3. EVT implication. There must be a min and max between 1 and 5, but doesn't have to be any of the given values. We don't know what happens between 1 and 2. We don't know what happens at 1.5. We don't know what's at 2 and 4, exactly what happens. Now, it doesn't need me, yes, it went from -1 to 3, which means that the function increased on average during that interval, but it doesn't mean it happens. So, 5 is not certain. No, what I mean, 5 which is f of 4, could be the max, but doesn't have to be. Similarly, -6, which is f of 5, could be the min, but doesn't have to be. We don't know what happens for the values, for any of those other values that are not given for the tables. This is not the candidates test. We do not know that those are the only places where the derivative is 0. Now, if you were told that those were the only values where the derivative was equal to 0 and the function was continuous, then it must be true. Okay? If told f of x continuous on 1 to 5 and only critical points, which is where f prime equals 0 occurs at given values, then 5 and -6 are the absolute extrema. Okay, so it's a lot of like playing back and forth. So what I'm telling you here, and what happens a lot in these problems, is they just give you table values and they'll just say continuity. All right, or they'll say twice differentiable, which means continuous. And what we need to know is that EVT doesn't necessarily apply to those values unless I told you that those are the only critical points, where those were the only values where the derivative was equal to 0. If I told you that these values were the only values, if I told you that x equals 5 or x equals 4, f prime of 4 and f prime of 2 equals 0, and those were the only places, then the max and min have to happen at those values. But because I typically don't give that to you, you don't do them. So a lot of these answers will be looking like they want to trick you. They want to make you believe and answer in the multiple choice. It's because it's a multiple choice. And they say, which of the following must be true? And then it could be just a simple A, B, C, D question. But sometimes they have it as 1, 2, and 3. Which of the 3 are true? And the answer could be 1, 2, only 1, only 2, only 3, 1 and 2, 2 and 3, 1, 2, and 3. All right, and they might say something like, oh, the maximum is. And you got to be like, well, they didn't tell me that these are only critical points, so those don't have to be the maximums and minimums. The function could go higher, the function could go lower. I don't know. All right. So my premise here is that everything is mostly in tonight's homework, especially it's on things that could be true, but doesn't necessarily have to be true. So let's do an example. Let's take that same table. So I'm going to tell you that f of x is twice differentiable on the interval 1 to 5. And all twice differentiable means is that it's continuous and there's no sharp turns. So in other words, f prime never is undefined. That's basically what it's saying. That's what this says, okay? Twice differentiable, just make sure to say f prime is not undefined and that the function is continuous. It's continuous and the derivative is never undefined. That's all we need to know. There's no sharp turns and everything connects. So x, f of x, and what are the values? I gave you 1, 2, 4, and 5. 1, 2, 4, and 5. And negative 1, 3, 5, negative 6. Now, some of these problems, like I was kind of talking about in terms of, I'm not going to try to apply any IVTs or MVTs into today's problems. I did want to bring out the top one in terms of things that may not be true. But our focus is going to be on the slopes, okay? Our focus on these tonight's problems will be on slopes. And tomorrow we're going to work on these tables as well. I'm trying to lay the groundwork today and do some problems and do the meatier, more difficult problems in tomorrow. But the premises of what I've covered today will still apply for tomorrow. Okay. So we have a bunch of mini slopes. All right. So basically what we have is we talk about M1, M2, and M3. So in every one of these parts, most of these questions are going to ask you about the slopes. And we should be able to identify the slopes first and foremost. Now, some questions are going to ask you about slope values. Some questions are going to ask you about function values. How do you know the difference? I'll kind of talk about that tomorrow. It's based on the premise of the question. Just know that tonight's problems, you're going to focus on these little slopes right here. So when you're doing these problems, you're going to have to find each of the little slopes. All right. What's my first slope? Now, I know I've talked so much today. What's my first slope? Now it's time I need to hear back from you. How do I find that first slope? Algebra 1. Can I get a response? What is the slope from 1 to 2? From x equals 1 to x equals 2. Anybody? Yeah, basically. Yes, Norda. Some people like to see it as rise over run. I like to think of it as the quotient, the slope quotient. And we're just focusing on those first, we're just focusing on these values right here. Correct. Now you should, so notice that so the way we would do it is the outputs, the difference of the outputs, delta y over delta x. So remember m is delta y over delta x. So we get 3 minus negative 1 over 2 minus 1, which is 4 over 1, which is 4. Okay. What's my next slope? 1. Thank you. So it's 5 minus 3 over 4 minus 2, which is 2 over 2, which is 1. What's my next slope? Yeah. So I have negative 6 minus 5 over 5 minus 4, which is negative 11. All right, so my slopes go from 4 to 1 to negative 11. Okay? Now, I can also think about these slopes, and the slope it decreased and decreased again for the slopes. All right, so first and foremost, what do I know? Can f prime of x be greater than 0 for 1 less than x less than 5? Explain. Can the slope, or is, I want to say is f prime of x greater than 0 for all values between 1 and 5? Yes or no? Come on, we got to get some participation to really get this going, everybody. Is the slope positive everywhere? Basically, the answers are yes, no, and possibly. The answer is no. Thank you. No. And the reason is because the slope is equal to negative 11 between, on the interval 4 to 5. So on the interval 4 to 5, it's negative. So this is a no on that interval 1 to 5. Okay. B. Is f prime of x greater than 0 for 1 less than x less than 5? Oh, sorry, less than 4. Explain. Is the slope positive between 1 and 4? Yes, no, possibly. I have a direct message. No. Not that response. Not that response. Another one. This one's a tricky one. So I had multiple people say yes. And the actual answer is, this is a possibly. Yeah, there's Judy. This one's a possibly. Well, M1 is 4 and M2 is 1. Between each of the two partitions, f of x could have changed slopes within just the average slope. So what do I mean by this one? So for example, let me give you like a small table here, or kind of graph. I have x equals 1, 2, and 4, and the value is -1, 3, and 5. So let's say those are the values. And you would think if you just looked at it and go, oh, the function's increasing. It goes from -1 to 3 to 5. And it looks like it's increasing, but we don't know what happens in between. This function could be going up and then down, up, then down, then up. This is the premise of NVT technically, because all we know is that the function will end up going from here to here, and then the function will end up going from here to here. So the mistake that people think is that it has to go directly in a straight line from x equals -1, or from x equals 1 to x equals 2. We think it has to go in a direct line from 1 to 2. That's not true. And I want you have to think about those functions. It could have gone up and down and up and boom. And so if you look at this picture and the way I've drawn it, it's actually f prime is negative. It could be negative. It could be negative slopes. The slopes could be negative at some points inside each of these intervals. We don't know, and that's the hardest, that's the big thing about today. What we know and what we don't know. We know that on average it goes up, so it could be true. It could be true, possibly. Could be true. But it doesn't have to be true. Over here, we know it can't be true because we have something that breaks it. So sometimes something breaks it and it says, and it's like statistics. For those of you who've taken statistics with me, we know it can't be true, versus just because you have a bunch of yeses doesn't mean something is true. You get a positive, and a positive. It doesn't mean it has to be true. But if you get one opposite, then you know it's false. Okay? So, it could be true. C. And most of them are going to talk about the idea, based on the values of these intervals, which of the following could be true. Okay? Let's talk about the second slope. Is f double prime of x greater than 0 for 1 less than x less than 5? No, actually I meant to say less than 0. Can this be true? Well, in this instance, for this type of question, we need to look at the slope of the slope. And what this is saying here is saying, is slope decreasing? The second derivative being negative means that the slope, f prime, or the m's, is decreasing. So it's still, that's why we're still doing on the same topic here. Is the slope decreasing? Well, we found the slopes for 1, -11. Now, I'm not talking about the value of the slopes. I'm asking you for how the slopes are changing. So the slope went from a +4 slope to a 1 slope to a -11 slope. Now, slope 2 is still positive. Slope 1 is positive. But it went from a bigger positive to a smaller positives. So, are the slopes decreasing? Yes, no, could be, possibly. I'm still getting you guys. Based on the values given, yes. but the answer is possibly. Well, so most of you are saying yes again. The answer really is possibly. While the slopes are decreasing for the table values given. However, once again, within each interval, the slopes could be changing. Okay, so you want to say yes. You want to say yes. And depending on how the question is worded, the answer could be yes. All right. The slope went from decreasing to decreasing. Or the slopes decreased twice. So the slopes went from 4 to 1 to negative 11. So the slopes could, and based on these values, the slopes are decreasing. But just like this image right here, we don't know what is happening between 1 and 2. We don't know what is happening between 2 and 4. We don't know what is happening between 4 and 5. We know that it's changing. And if we were to kind of, it could be such that this is concave down. It could be that this is, the graph is actually doing something like this. It could be doing that. It could be concave down the entire time, but it doesn't mean it has to be. That's the biggest problem. So when you're doing the problems, and if you get something wrong, you got to think about that. Now, some of the questions are worded such that which of the following could be true. So if this problem stated, if problem C, could this be true, then the answer would be, give me a response. If the question was worded as, could this be true, then we would say yes. We would say yes.
Wait, I'm confused because didn't you say that if there's two positives, right, it could be, but as soon as there's negative, it's no longer?
We're talking about for question C about the slopes decreasing.
Oh.
So it could. That's why I said possibly. So the answer possibly turns into a yes in that type of question, because based on the given values, it's yes. So if I said, could f double prime be less than 0? The answer is yes. But if the question says, is f double prime of 0 less than 0? Then the answer is possibly, because we don't know for certain, but we know it could be true. Same thing for here. Are the slopes positive between 1 and 4? Well, positive, the first two slopes are positive, so it could be true. So, and the same thing goes for, but however, for question A, when we're looking at the slopes for 1 to 5, it can't be true. So, could f prime be positive between the intervals 1 to 5? The answer is no, because something broke it. So, on your homework and on the AP exam, typically ask, which of the following could be true? So that's how the AP exam typically answers it. Which of the following could be true? And in that case, question A or question B and question C, those would be yeses. It could be true based on the table values, based on the slopes. It could be true. Now, it doesn't mean it has to be true. And that's what I want to focus in terms of the lesson. It doesn't have to be true for part B and part C, but it could be true. I guess I've used the word possibly, but I can, once again, could be true, but doesn't have to be true. There's a lot of questions I give that they really try to take you out on those, and that's what you're really going to focus on tonight's Delta Math homework assignment. Which of the following could be true, or explaining why something doesn't have to be true. That's what I have for you for today. Really work on these. You have Delta Math again coming up for you tomorrow as well, but focusing again once on tables and this idea of could be true type of ideas or must be true. So what has to be true, what could be true, and focusing more on the actual IVT, NVT, and EVT for tomorrow's problems. So get that practice. I know you're just wrapping your head around them, and this is more theory than just problem solving. Don't worry. For those of you like taking derivatives and setting things equal to zero, we'll get back to you pretty soon. All right. But right now we have to focus a little bit more on theory before we get there. That's what I have for you. It's 9 o'clock. See you tomorrow.